Hey guys, welcome to another video in our Back to Basics series. Today we're going to be looking at some relays, so hooray! How to play with relays. Now relays are pretty straightforward, for those of you that don't know. I mean, you give them voltage, they're made up of a coil. I guess we'll explain mechanics of them first. If you can see, you can see my cursor very well, but they have a coil, and it's basically a solenoidal action that happens. Basically, you apply voltage and push current through the coil. The current then creates a magnetic field that then pulls a plunger down, which then usually moves some sort of mechanical arm that closes in a set of points. And then those set of points you then hook up to whatever. They're fairly low resistance, usually in the milliohms, but they are a mechanical device, unlike transistors and things like that operate on the principle of the flows of electrons and creating a flow and whatnot. If you want to see how transistors work or whatever, those of you that might be new to the series, check out the my transistor ones. I think I've done both bipolar junction transistors, or BJTs, or in the industry just called transistors. And I've also done the MOSFETs, or metal oxide semiconducting field effect transistors, which are made up differently. But they are what's called solid state devices. These are not solid state devices because they're an actual mechanical device. You push current through them just the same as, like, let's say a BJT. You push current through their base and it makes it turn on, but this physically moves. It has friction and it can wear down after a while. They usually have ratings, which I'll show you, and there are some drawbacks to them so far as, like I said, they can wear out. They have friction. They can only be actuated so many times before they start to degrade and then they break. And then there's also other little pitfalls that we're going to get into with this, so far as, like, let's see, they call it backscattering or back EMF, or basically you creating voltage spikes and things like that with these things can do that to you. They can create inrush currents and burn things up. I mean, there's a lot of pitfalls that you need to be aware of when you're designing relays, especially when you're playing with relays with microelectronic circuitry. Now, relays are on everything. I mean, relays are in your furnace, your humidifier, sort of. It's a solenoidal cell, but it's the same principle. Relays are in many different things, and you can sometimes hear them clicking. Your car is full of relays. Those are called cube relays, but the automotive relays, if any of you ever had to replace one of those, sometimes that can be a headache trying to find. It's not a fuse, it's a relay. They're the little square boxes that are inside your fuse box. Anyway, relays are everywhere. They're very, very easy. They're usually fairly inexpensive, and the thing that's great is they're inexpensive for what they can handle. Like this one, for instance, these guys can do 8 to 10 to 16 amps, and these are little PCB mount micro miniatures, and we'll probably do a demo video and I'll show you what they look like, but they're very small. If you look down in here, I mean, you can look at this. They're I think this is in millimeters, I believe it's in millimeters, so 29 millimeters by 25 by 12.4. I mean, these things are fairly small. I mean, so it's basically about an inch. It's about an inch square. It's rectangular, but more or less it's about an inch square. They're very tiny, but yet very powerful. You can push 16 amps at like 100 and some volts through their little contacts here, and they take it just fine. So very powerful little devices. And also, so that's one of the key features, as well as you have isolation. That's another huge benefit of a relay, why you would want to choose it over a transistor. Since transistors are done by way of charge and moving charge from one area to another, it's not a totally isolated, like an actual cut in the circuit, like where the circuit is completely severed. Relay is, because literally the contacts move apart from each other, so it literally severs the connection. So in certain circumstances, I know in certain, I think it's audio correct me if I'm wrong. I think there's certain audio things, because I had a friend that was doing some stuff with audio, and he needed that actual physical isolation when he switched between, I can't remember, amplifiers or something. He could not use transistors because they would bleed, they would leak, they'd turn off sort of, but they'd still let, because of the high power that he was working with, it would still push through the transistor, even though, and then there was also magnetic issues and all kinds of stuff. Whereas these guys they're not really susceptible to magnetic interference. You can blast these with real high magnetic fields and RF frequencies and stuff, and usually they're pretty robust. They're not going to do anything. So that's another benefit to relays. So there's good and bad, just like with transistors. There's good and bad with them. Okay, what we're going to look at is the one that I'm going to be probably demoing is this guy over here. He's a 2-pole, which those of you that don't know what poles mean, it's how many switching contacts you have in there. So this one has one, and as you can see from this little diagram, we'll zoom in real close. This is the diagram for the coil. So this is the coil. This is what you'll and it doesn't matter because it's literally just a winding of wire. So it's kind of like a resistor, sort of. Except it does have a very large inductance in it, and I'll show you what that means here in a minute. But basically, you're going to, let's say, take this end to ground. You'll ground this end, and you'll put whatever the rated voltage for this coil is. And I believe for this one, it can be 6 or 12, or you can get it in many different voltages. The one that I have on hand here is 6 volts, so you can only put 6 volts through this. You don't need to put any type of resistors on this or anything, because since it's a coil of wire, it is its own resistor in effect, so it'll only draw the current that's going to draw, and the current is defined in here how much these guys draw when they turn on. So like I said, you just literally give them voltage and they work. So you don't have to worry about, kind of like with BJTs and stuff, you got to limit the current to the base and things like that with the limiting resistor and things. You don't have to worry about any of that with a relay. You just give it voltage. It'll take a certain predefined amount of current because of its own internal resistance, and you're good to go, and it works. Anyway, here is the actuating. Now, this guy is what's called a double throw. Some of you guys have seen that Spdt or whatever. That stands for single pole double throw. And that means that you have a set of normally closed points, which means, see, as you can see, this is normally closed right here, which means in the de-energized I guess you'd say state, the de-energized state, these two pins are connected together. Then in the energized state, when you energize this, it will then switch, which will then break this connection here and make the other connection between pins 11 and 14, and then break 11 and 12. So 11 is what's called the common point, because it's common to both of these. Now this one is normally closed to the 12, and normally open to the 14. That's what normally closed, normally open means. Those of you that haven't messed with relays, that's what that means. You'll see an NO and an N. You'll see an NO and an NC. NC doesn't mean not connected, and NO doesn't mean the word no. It means normally open and normally closed. NC and NO. So that's what that means. Anyway, on this guy, he is just what's called a single pole. He has one single common, but is a double throw because he has two states that he can be in, whether he's energized or not. He can either be in normally closed or normally open. So that's what that is. Now, if we swing on over, let me grab my hand tool. We swing on over, so there's another single pole double throw. But we swing on over to this crazy guy, this craziness, same thing. You've got your coil right here. But this guy is a DPDT, which I don't know if anybody can guess what that is double pole, double throw, is what that means. Which means you now have two poles, because if you look here, they split the relay in a different way. You've got one pole here, because you have one common point between these 2 points. And then they have another pole here, because you have another common point between these 2 points. So you have common points 11 and 21, and 11 is common between 12 and 14, and 21 is common between 22 and 24. Now, they both have normally closed NO and NC for normally closed, and NO for normally open. The normally open side is shown with pins 14 and 24, and the normally closed is pins 12 and 22. So, pretty straightforward, right? Relays aren't too complicated, especially when they give you these nice little diagrams, and most all relays that I've ever seen gives you these little diagrams that help you visualize what's going on. Sometimes it's literally just words. They'll tell you pins such and such and such and such are normally closed and such and such are normally open, and 11 and 21 are common, and it's literally just spelled out, and those are can get confusing. But the majority of them have little diagrams like this that will show you what they are. Then we also have our footprints, that show you what pins are where and the spacings and everything, so you can make your decals and whatever. They also, I think these even come with socket, via screw and rail mount, 35 millimeter rail mount, which means is that they have a little base thing. There'll be a little plastic thing that can snap on to a 35 millimeter rail, which I don't know if you've seen DIN rail, but DIN rail. It's a railing that you can screw on to something and then snap these bases onto, and then these relays plug into those bases. But anyway, that's a whole nother topic. Anyway, if we get down here, and see, here we go. There's the Spdt and Dpdt. So single pole double throw and double pole double throw. So pretty straightforward. That's what that means. So we've got all of our current ratings and whatnot. So this is telling you your max peak current. See, this is contact specifications. This is how much you can this thing can switch. Now, a good point to bring up here, and I didn't know until I got really into relays because of selecting certain things in certain projects, but there's DC and AC ratings on these guys. And there is a difference in other relays, like these, for example, I think are just DC, so it's got the DC amperage. Does it have an AC amperage? Doesn't look like it has a peak current. That's peak current rating, but I think it's just going to give me DC. It's not going to give me AC. There's rated power, because these guys, some of their coils, you can get AC/DC coils, which they'll run off of either, and like I said, an AC current, AC voltages or DC voltages. But I think they're showing the points being rated for DC. The difference between, and there is a difference. Most people think, AC or DC, an amp's an amp, it doesn't matter. Well, yes and no. Yes, an amp, pretty much an amp is an amp. Really, if you want to get down to brass tacks, a watt is a watt. Okay, is really the thing. If you're wanting to really compare apples to apples, regardless of the voltage, regardless of the amperage, no matter what their relationships are to each other, is wattage. Really, power is the thing that is universal, because power is joules per second. And I don't care whether you've got an AC voltage, you've got a DC voltage, you've got, an AC amperage or a DC amperage, or it doesn't. Power doesn't matter. Power is energy versus time is what it is. So how much energy moves in a given period of time. That's what wattage is. And so if you really want to compare apples to apples, look at wattages. But really, the thing that matters with relays and contact ratings is when if it's an AC contact rating, they're expecting the AC waveform eventually crosses the zero threshold. In fact, I'm going to see if I can't illustrate this for you. I know my illustrations are sometimes horrible, but we're gonna give it a shot. How big can? Oh, perfect, nice and big. Okay, so if we add an AC waveform, oh gosh, this is gonna be horrible because I'm drawing this with my mouse, but it goes up, right, and goes down. Well, that ain't half bad. Well, right there, it's 0, right? And 0 volts. So essentially, if you've got something that's a resistive load, let's say it's just resistive, the current is going to follow the same profile, right? The current's going to be sinusoidal. Well, they know that eventually you're going to hit 0. So if I, let's say, stop, if I stop conducting somewhere around here, well, this voltage is going to eventually going to cross the zero threshold, and die out. It's going to quit. Whereas DC is different. Since DC looks, like this, it just goes up straight across. They're having to break when you break this and you say, okay, I want to shut it off. It's at its maximum. It's maximized up here. Whereas with AC, depending on how where you break it, you could be on the downward slope or whatever. So what they do is they actually derate the contacts. They'll actually rate them down a little bit on AC ones. The AC ones won't be as strong and robust as a DC set of contacts, because DC, they know that the power is full blast all the time. So a DC, if you're wanting, basically if you're wanting to get a relay and you're just digging through your barrel and you find a relay that you have laying around, you want to use it for something, if it's DC rated and its rating is what you need, but you're going to use it for an AC to switch an AC load, and then you're probably okay. So let's say it's a 5 amp AC current is what you're wanting to interrupt, and you've got a 10 amp relay, but it's DC. You're safe. You're fine. The other way around, I'd probably way overrate it. At least 50 to 70% overrate your deal. So if you had a 5 amp load again, but it was DC, I would trust a 10 amp, maybe a 15 amp AC relay, because the AC contacts will be rated, they won't be as strong because of that, knowing that AC current will eventually reach zero, and they let the rating slide a little bit on those and don't make the contacts as robust. So what'll happen is, it's not like it'll explode or something terrible would happen. What will happen is, just over time, the arcing that will happen inside the relay as it tries to break that current is it will end up corroding and carboning up the contacts and getting them where they won't make contact anymore. So when you want it to close, it won't complete the circuit. It'll be all carboned up and it won't work right. And sometimes you can actually melt them together, and then you reach another problem. You can't break the circuit that you're wanting to break because the contacts are actually melted together. So something to keep in mind. So always make sure you keep the right rated stuff for the right rated things. So AC goes with AC and DC goes with DC, and you won't have a problem. That's the easiest way to do it. So anyway, that's probably enough of the technical data. I mean, it's pretty straightforward. I mean, it's, you size them for what kind of load you're wanting to do. You look at what kind of current that the coil pulls, like down here with the current. Gives you an operating range. Yada, 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 yada. The voltages, see, these guys, you can pick all these different voltages. You can do whatever you want with them. Rated power, here's the wattage. They give you all the different watts depending on what you're doing with it. If it's AC, DC, or you're using a sense DC, they'll give you what rated power you're dealing with. So it looks like they're not going to give you the amperage, though, of the coil. Maybe they'll tell you up here. If they don't, you know the power, so you can calculate the amperage. Well, it looks like they're not going to have it. So what you can do is, down here you got the rated power. Which that means, this rated power means that this coil would dissipate this much power. So if we're using a DC coil, let's say we're using DC, select it. So we're using DC, we're going to use that center one. So this guy is about 650 milliwatts is what this guy will do. So you take whatever voltage you have. So if we're for 6 volts, let's see, we are 0.65 by 6 volts, you're at about 108 milliamps. So you're at about 108 milliamps is what this guy's going to pull. So you need to make sure that I would not run a relay straight off a GPIO pin. I don't care if you do find a relay that's small enough that it's below, let's say for the PIC micros that we've been using, 90 milliamps, find one that's like maybe 20 milliamps or something like that. I still would not run a relay straight off a GPIO pin. I would buffer it with a transistor, and I'll show you why. I'll show you why here in a minute. And in fact, actually, I think I'll show you why right now. Great example I can do is just do an LT Spice. Those of you that don't know what LT Spice is, oh man, if you're in electronics, you got to use this because this uses the Berkeley Spice algorithm. This is totally free. You download it from Linear Technology. Totally free software. I have a whole series on how to use this software, just the basics of how to use it. It is phenomenal software. It can save you a lot of headaches when you're trying to put something together because you can simulate it first here and kind of get the gist of what it's going to do before you actually put it together, and it's doing squirrely stuff and you have no clue what's going on. This will give you kind of an idea of some pitfalls that you might run into. So what I've done is over here I've created our circuit. I've got a 6-volt supply. I've got a resistor and inductor because a solenoid, or whenever you wrap wire around a ferromagnetic post, you create an inductor, right? I mean, that's what an inductor is it's a ferromagnetic post, usually iron or what is it? Was it carbon? Some of them are carbon. I don't know. They have different. There's multiple different cores, but a lot of them are iron or ferrite or something like that. And you wrap wire around it, and then that stores energy in the magnetic field. So anyway, so the B field. Anyway, so it's got some inductance to it, and quite a bit usually. Now here I'm exaggerating just to illustrate a point. I think those relays probably aren't this bad. I've never measured one, but I doubt they're this bad just due to the fact they're so small. But I'm exaggerating by saying 5 millihenries. That's quite a bit, actually, believe it or not. So we've got our inductor, and then here's our transistor. This would be like if we were, like I said, buffering it with a transistor. So here's our transistor, there's our bleeding resistor, and then this represents kind of like our microcontroller. I just put a 5-volt power supply that I'm going to turn on and off. This PWL, what this does, I'll show you guys. You can basically make PWM waves. You do a piecewise linear is what it does. And so basically I'm saying initially for 0 seconds, I want it to be 5 volts. I want it to be on. Then after 5 milliseconds, I want it to still be 5 volts. But then after 5 milliseconds and 1 microsecond, so 5.001 milliseconds, I want it to switch to 0. So really fast. The reason that I don't just say, after 5 milliseconds switch it to 0 is because it will actually ramp it down over the course of 5 milliseconds is what it will do. You'll actually get a ramp function. That's not what I want. I want a sharp turn off. And so I say that it's on for 5 milliseconds, and then after 1 microsecond past 5 milliseconds, it becomes 0. So that way it shuts off in a microsecond. It's really quick. And you'll see what I'm saying here in a minute. So I'm going to go ahead and run this. And just to show you what kind of signal I'm putting out here, I'm going to go ahead and I'll show you it. So see what I'm saying? You've got, it's 5 volts up here, and then after, 5.001 milliseconds, it just slams down to 0. I'll show you what I'm talking about. If I just let me take this out, and I just say, after 5 milliseconds, I want 0. If I do that, it'll ramp it over 5 milliseconds. See? So over the 5 milliseconds, it's actually ramping it down. And that's not what I want. I want the other one. So I'm going to undo that and go back. There we go. I want a sharp drop off. So anyway, so that's how to configure that, just in case if you're wondering. So all right, I'm going to get rid of this. So let's delete that trace and get rid of it. Rerun it just to make sure we don't have any errors. Now, what I want to look at is I want to look at the voltage across our transistor, because due to this inductor, you're going to get TV guys know this, TV repairist guys, the tube TV guys know this is backscatter or the flyback. There's actually complete converters called flyback converters that are designed around this principle. Whenever you collapse the field around an inductor, which means you remove the voltage on it, so the magnetic field collapses inside of the core, it will actually cause an overshoot in voltage. Okay, and especially like what we're doing, we're removing the ground. So when we take loose the ground and we break the current flowing through this, it's going to actually induce a voltage spike, and it's called an inductive spike. that will overshoot the voltage past 6 volts. It'll go above 6 volts. Now, depending on how many henries this is, whether it's 10 millihenries or God forbid be a henry or something like that, depending on how large this is, how large the current was going through it, and the voltage level, it could even be kilovolts. And that's how flyback converters work, is they'll use a small voltage on something, but yet have a huge amount of inductance in something. Usually it's like a transformer, or it's like a 1-to-1 transformer or something like that on a flyback converter. And what they do is that they will switch, let's say like a transistor or something, they'll switch the current through it at a certain frequency, and they will get kilovolts at that frequency, or at a similar, and they can filter the frequency to get a kilovolt waveform to fire a cathode ray tube. And those are called flyback converters. So anyway, there's a brief little history lesson. Anyway, we're going to see that when I do this. So I'm going to, let's see, it's simulated, it's ran. Okay, I'm going to measure my voltage. Oh, if I can get my probe in there. Voltage. Oops, that's current. I don't want current. So we see that the current shuts off, so that's good. The transistor's working. I don't want current though, I want the voltage. There we go, voltage from there to there. I want the drain to source. Now look at this. It's 6 volts, but see right when it switches, like here, let me put the current up here so you can see it. Here's the current, travel along, 240 microamps, whoops. And then the current, boom, all of a sudden goes to 0. Let me zoom in. I'll show you what I'm talking about. Let me zoom in here. Look at this. You travel along at 6 volts, and then all of a sudden you start to go down, and whoa, and then when it reaches the bottom, it goes, whoa, and we're shooting clear up to 10 volts. Now, if this transistor is only rated for like 10 volts or something like that, or close to, which I probably should have done this more realistic with a different, I could probably do, I don't know, probably 8 millihenries or something like that and get it up to around 20 volts or so, which is pretty standard for a transistor. You're gonna destroy this transistor. What's gonna happen is you're not going to melt the channel, it'll punch through the gate of the transistor. You'll actually, when a transistor fails, usually due to overvoltage, it will actually short the drain to the gate and the gate to the source. Usually it's gate to source. It'll short gate to source when that happens. It will actually blast through the silicon and actually puncture a hole through it and melt those two connections together internally inside the package. So basically, this is bad. This is very bad. So what do we do to fix this? How do we stop this guy from doing this? Well, we could find a different relay. That's a good point. We could find a different relay. Has lower inductance. That's a good fix. But what happens when you've got to have the inductor that the relay that you've chosen? You have to have that. Well, a neat little trick that you can do is you can insert a diode. I'll show you how this works. You place a diode across the coil of your relay. Okay, I'm going to pick one. Let's pick, I don't know. That guy looks good. Whatever, little Schottky. I probably wouldn't pick a Schottky for this guy. I'd probably pick, I don't know, maybe a 1N4007 or something like that. I don't know, simple one that you can get a hold of. But you want your diode to be the current rated for this guy, and you want it to be close to the voltage. You want it to be close to the voltage that this guy is going to be. So 6 volts, so you'd want maybe 10, maybe 20 volt, probably make it similar to your transistor. Put like a 20 volter in there. I think that's what this guy was. This guy was 20 volts. You can maybe get that a little tighter. Maybe do it if you can find a 10 volt one, that might work better. But watch what happens. I'll zoom in on this. Look at this. We went from 10 volts to 6.8, so we rose 3/4 of a millivolt now instead of the other way. See how much better that made that? We were punching 10 volts. Now all of a sudden we're pretty much back around where our 6 volts is. Our spike is less. So there is a very good trick, and you almost always will see that whenever using relays and microelectronics combined, or even inductors. Sometimes you can have, let's say you just have an inductance, maybe you've got big long cables that are connecting something up, and you're switching the current through those big cables, and you're tearing up your electronics, can't figure out why. That's probably what's going on, is you're getting an inductive overspike, just like in a relay. Because when you use big, huge cables, like number 4 gauge copper wire, and it's really long, everything has inductance per unit length. I can't remember. There is a rough rule of thumb number. I can't remember what it is, but it's like so many. I think it's like 10 nanohenries per inch or something like that of was it 20 gauge or no 18 gauge wire or something like that. Like 18 gauge wire has somewhere around 10 nanohenries per unit length or something like that. So you get the wire really long, like you're winding a transformer or something like that with it. You get it really long, you get a lot of inductance there built up. So that is something to watch out for. So this is definitely a pitfall of relays that you can find. That is the biggest one, and that's the main thing I wanted to show you about. The reason I wanted to make this video and stuff is I wanted to show you because I did not know that. And I remember I was doing a project one time, and we were just tearing transistors up. They were failing left and right and left and right and left and right. And what we ended up doing was putting in almost like a, I don't know, it was like a power systems grade one, which was hugely expensive. And it was gigantic, that could take, and what we didn't know is it was that overspike was just destroying everything. And so, but it was just that overspike was just destroying it. And we didn't know that. And I mean, I was ignorant, I was new, fresh out of college and all that stuff. And so I didn't know about this. And it wasn't until I met another engineer that let me on to, whoa, why don't you have diodes on that? And I said, diodes? Why would you put a diode across that? It serves no purpose. Oh, but it does. And so then there you go, and just as plain as it can be, that's exactly what's happening, is you're getting an inductive overspike. So guys, I'm sorry this video probably took a really long time, but I wanted to really go through it thoroughly for you guys and let you guys get a good grasp of good old-fashioned relays, because relays are wonderful. Like I said, they're usually, especially the PCB type, they're fairly cheap, easy to get a hold of, and they work really well. So guys, thank you for watching. I'll probably do a demo video, might as well, and I'll hook one of these up just so you can see it working. Those of you that might be brand new to electronics and have never really worked with relays or never really seen how they work. These little finder relays I find, no pun intended, these finder relays I find are kind of cool for beginners because they're clear. They are clear. Like, let me go back. They're clear. See, they come in clear packaging, so you can actually see them actuate. You can see them wiggle and move and do their thing, which is very cool if you've never seen, how these actually work inside. If you've always seen, let's say, like the automotive type that are in your car, they're just black. They have a black opaque casing on them where you can't see the insides and see what it's doing. So these are a cool little relay, so I highly recommend them. You can get them at, I think, New Arc sells them, all those places that are on my channel. If you haven't checked out my channel, please stop by, check it out. There's tons of videos there, lots of good stuff to check out. Other than this, check out the basic Back to Basics series. I'll probably be, if I haven't already, creating a playlist that has all these in it. I think I've already created that, but if I haven't, I'll check and I'll put it up. But check out the series. There's lots of good stuff. We've got stuff about diodes and sizing diodes and Zener diodes and all that stuff, as well as doing transistors, both the bipolar junction transistors and the MOSFETs, the field effect ones, and all that fun stuff. So please come by, check out the channel if you haven't already. Push the subscribe button if you like what you see, and please like and share these videos. Hell, really helps me out, helps me to buy more hardware and bring you guys cooler stuff and bring you guys what you guys would love to see and know how to work with. So please hit the like button, check it, and share it with your friends and whatnot. Share it with forums even, I don't care, and so that way we can keep on bringing you good stuff. Well guys, I'm out of time. That's it. Hope you guys enjoyed it, and for that, that ought to do it. We'll see you guys.